Because we're about to get going. My name is Pat Bruno. I'm an assistant professor at UC San Diego. I'll be chairing our session on light. Light turns out to be visible light communications for a bit, and then something else. Our first paper today is going to be TunnelLiFi, looking at bringing the performance and security advantages of visible light communication to the IoT realm with an efficient bridge between light-based communications and traditional radio. LiFi is being presented by Wenqing, who's unfortunately unable to clear visa issues, so it's going to be remote. She's a late-stage PhD student at Uppsala, nearing the end of their PhD, and would like to announce they're currently looking for postdocs. So if you're looking for a postdoc, you all should talk. But otherwise, I'm going to cede the floor to Wenqing and say we look forward to hearing about it.
Thanks a lot, Pat. So unfortunately, I cannot come to attend Tote Mumbai physically, but thanks Jeremy and Pat, so I can still present this work online. So my name is Wen Qing, and I'm from Uppsala University in Sweden. And in this presentation, I want to introduce our early stage work about a system which brings a LiFi to commodity like IoT devices. And this work is basically a collaboration with our co-authors from different universities, Spain, Berkeley, and also in US. And I will start the background story from LiFi. So light fidelity is a wireless technology that use visible light for data transmission. So the information is actually modulated on the light signal according to the baseband signal. And LiFi offers a bunch of the advantages, such as it use a different part of spectrum. So other than like crowded RF electromagnetic signals, they are using the light spectrum. And in addition, it can simultaneously provide illumination, energy, and communication, which makes it a good candidate for IoT, Internet of Things connectivity. So researchers are focusing on LiFi as a viable solution for the rapid growth of IoT to relax the high pressure on the radio spectrum. And IoT could be deemed as enhancement for the workability of IoT devices. There are already a bunch of the application scenario which depict an ideal blueprint where LiFi and existing IoT technologies can seamlessly cooperate each other and forming a very nice ecosystem. However, LiFi has yet to gain the widespread adoption. Several factors contribute to the slow adoption. And the first thing is LiFi technology requires changes to both the transmission and reception infrastructure. So current commercial LEDs, like they are this lightning fixtures, typically they're using for the illumination, and the lack of the necessary modulation circuit. So therefore, the first necessary step is retrofitting them to serve as a LiFi transmitter. And after that, we also need LiFi capable user devices. And IoT devices manufacturers need to add LiFi to their devices. And the modification of existing hardware cannot be avoided. In addition, like millions of IoT devices have already been deployed. So the inertia of an already mature market makes this process complex, costly, and time-consuming. And next, which is most importantly, LiFi suffers its own challenge, which is the coverage restriction. So LiFi signal cannot propagate through physical space, or light signal cannot. And things like walls, floors, or metals will block the light signal. So when considering privacy, is of course an advantage. But for IoT applications, it limits the scenario where the sensors may be located in places with poor light propagation. So how could we support LiFi adoption in IoT scenarios? Here are a few of our thoughts. And most IoT devices, they are still using the RF communication technologies, and they are deployed in our daily life. And to support the integration between LiFi and IoT devices, we kind of think about using a replication device that replicate the LiFi signals onto the radio waves. which then can be received by the radio transceivers in standard IoT devices. So here is a system overview. So light fixtures still transmits the light signals, which carries the data. Then we use a device. Ideally, it would be a small, cheap, and most importantly, energy efficient device to replicate the data in light signal onto radio waves. Then it can be received by this IoT device's radio receivers. Now the question is, how could we design such kind of replication device? So here is a conventional approach, which is a straightforward approach. So we need a pipeline architecture like this. And first we need a photodiode, tracks the changes in light intensity. Then the signal needs, because we use photodiode, so the generated signal is weak, we need to amplify it by a transimpedance amplifier. And after passing through several processing blocks, an ADC will translate this amplified signal to the digital domain. And it's followed by a demodulation process to recover the LiFi baseband information. And finally, a radio transmitter transmits this information over the radio waves and radiate out from the antenna. So this design, however, requires several energy-intensive components marked as red, such as several amplifiers, ADCs, and of course, radio transmitters. So which makes this design power hungry, at least a few million watts. Furthermore, each LiFi modulation scheme would need a different demodulators plus different radio transmitters. And another challenge would be that each step in this pipeline may add a delay between the communication of the LiFi transmitter and IoT devices. So to tackle these challenges, we propose our system, TunnelLiFi, which simplifies this pipeline architecture. And here's a summary of the properties that our design can achieve. So we designed the system, it can replicate the signal from light to RF at the peak power draw under 100 microwatts. And it can operate in low light conditions down to 300 lux. And in addition, it does not add delay while doing this replication. So next, I will move on to the main content and elaborate the design details. So this design relies on a component named TunnelDiode. They are quite popular more than half century back, but now they are not that commonly used for commercial purpose. And a special physical phenomenon called quantum tunneling brings this component an interesting negative resistance property. And this property can explain using this IV curve. In this IV curve, there is a region when the voltage increases, but the current passing through this component decreases. And more important, for TunnelDiode, this region happens at low bias voltages and currents, which actually means low power. In addition, TunnelDiode components operate really well at RF spectrum. So these properties make them useful for designing low power RF circuits such as oscillators, amplifiers, and so on. And referring to previous work Judo, I list reference here, in TunnelLiFi, we use TunnelDiode matching with a LC tank circuit to create an oscillator. And we can generate a carrier signal in the sub-gigahertz frequency band under 100 microwatts. However, this oscillator are very sensitive when direct attaching antenna to it. So as introduced in Judo, when there are a lot of dynamics in the environment, an external carrier signal can enhance its stability via injection locking. And this component not only can make oscillator, it can also make the oscillator circuit function as a self-oscillating mixture, which I called SOM here, which means a single circuit generates a high frequency carrier signal that can be directly mixed with a low signal strength baseband signal. That's a special property. It can mix with a low signal strength baseband signal. So TunnelLiFi leverage this property and omits the usage of any power consuming amplifiers. Directly couple a photodiode with this self-oscillating mixture circuit to achieve the replication functionality. So in this spectrum, which is RF signal, mixed modulated signal generated by this TunnelLiFi tag, we can observe there is a carrier signal. In this case, is 222 megahertz in the middle, and the modulated signal at an offset frequency, which depends on the LiFi baseband signal. For example, here, the LiFi signal is 1 megahertz. So the modulated signal is 222 plus 1, and its mirror image minus 1. So, and here is like the schematic of our TunnelLiFi tag or TunnelLiFi design. First, we modulate the LiFi transmitter with the baseband signal. And using a tunnel diode, a tunnel diode circuit, we can generate a high frequency carrier at the sub-gigahertz frequency band. And the LiFi transmission received by this photodiode directly coupled to the circuit, SOM circuit. And due to the SOM properties, the baseband LiFi signal can directly mix with this locally generated RF carrier signals and achieving mixing functions. And finally, the mixed signals is read from the antennas, and it can be received by a commodity receiver. And here's a photo of the TunnelLiFi prototype, and its size is similar to a €1 coin size. Then we move on to the evaluation. So the first things we investigate is the impact of the modulation frequency, which is the frequency of the digital baseband signal controlling the LiFi transmitter. And we keep the illuminance at 800 lux and varies the LiFi signal baseband frequency from 200 kHz to 2.4 megahertz. And then we measured the modulated RF signal strength with a spectrum analyzer. The result shows our design can support frequency up to 2.4 megahertz. And if translating to bit rate in, for example, on-off key modulation, it is 4.8 megabits per second. And then we investigate the light intensity impact. To change the optical power that photodiode receives, we change the distance between the LiFi transmitter and the TunnelLiFi tag. And we use light sensors putting aside the tag to as a reference to read the illuminance level. And we keep the LiFi baseband signal at 1 megahertz. The same, we measure the modulated RF signal strength using a spectrum analyzer. And the result shows the light intensity is proportional to the strength of modulated signal. And a high light intensity will generate a strong photodiode current, which enhances the strength of the modulated RF signal. Finally, putting everything together, we evaluate the TunnelLiFi system replication capability with this link quality experiment. And we conduct the experiment in an office room at the university. So the receiver, we use a CC1310 launchpad. And the setup is as below, and we change the position of the receiver from 2 meters to 12 meters away from the TunnelLiFi tag. And in this early experiment or early setup, we just investigate a simple 2FSK modulation without any encoding mechanisms and at a low bit rate of 2.93 kbps per second. And we use two metrics. One is a bit error rate, and another is received signal strength as a link quality matrix. So the result shows like TunnelLiFi is capable to replicate the data from the light to RF that it can be received by the commodity radio. And the link matrix, of course, will deteriorate when the distance between the tag and the receiver is longer. And finally, let me conclude this presentation. First of all, this is an early stage work, and we made attempt of designing a low power LiFi to RF bridge that can replicate LiFi signal onto RF radio waves. So our designs achieve these functionalities within below 100 microwatts, and it can work in low light conditions down to 300 lux. And we expect a design like TunnelLiFi would help LiFi to overcome the obstacles and facilitate its adoption in IoT applications. That's all for my presentation. Thank you for listening.
Thank you very much, and I'm happy to invite anybody who has any questions to come up and ask them at this time. And while you're thinking about questions, I had one. I wanted to ask if you had thoughts on which classes of modulation you think you could eventually expand this technique to, and if there are common modulation techniques you think would never be feasible with this kind of light to radio bridge idea.
So we have some investigation about like LoRa, like chirp modulation, and that works. And we also like FSK, like frequency modulation, of course, and amplitude modulation also will works, but that's not for LiFi. Like the one challenging things maybe a little bit will be phase modulation. But we haven't tried, for example, because one thing we need to notice, like, as I said, like this tunnel diode oscillators, when it runs without the carrier signals, it will slightly noisy. So this noise also, phase noise also included. So for phase modulation, that would be the challenge we need to overcome. But we haven't tried, for example, if we have external signals and a phase modulation, would that will make like an improvement for the performance that we haven't make attempt to investigate that aspect.
Okay, thank you for your good work. I have one question. I saw the between the transmitter and the receiver, the distance is 0.5 meter.
Yeah.
So my question is, in your experiment, what's the longest distance you can achieve? Do you consider this a limitation since you use LiFi and also radio frequency, right? So basically, it's combine both together. Yeah, sometimes I feel that is probably make a system more complex. Yeah. Do you feel that is this limitation? Thank you.
Yeah. So so as we tested before, right, in these figures, so actually we support 300 lux. That is the lowest we tested, and but this experiment, like the light intensity had here is 600 lux, so we can be further than this short distance for sure, but it's just the boundary is 300 lux now. And the distance between these two, it depends on several parameters. For example, your strength of the light signal also will impact the distance for the between the receivers and your tag. So if you have a strong condition, this can be extended further. But how further, that's need to more experiment to really get the real like result about that.
Okay, thank you.
All right, thank you very much. Let's thank our speaker one more time.